In this screencast, I'll give a few tips on using CodeGrinder for the ARM assembly assignments. So here I am, I've logged into Leghorn. I have grind set up and logged in. If I do grind list, I see my assignments, and down here is my Mandelbrot assignment for CS2810. I'm going to go and get it, so grind get, and I see my ID number here is 288. I could also type the full name of the assignment up here, but 288's easier, so I'm just going to type that. That unpacks the problem set into CS2810/CS2810-ARM-Mandelbrot. If I had multiple projects in the same class, they would all be under the same main directory, and then each assignment goes in its own subdirectory. So that's why there's two levels of directory structure there. Now the first thing I'm going to do is I'm going to put this all into a Git repository before I start anything. And I'm going to do it at the level of my course. You can do it on a per assignment basis. I find it more convenient to just do it once per course. For this one, it doesn't really matter very much, again, for if we only have a single assignment in the course. But to start out, I just type git init in the directory that I want to be the root of my project, so my CS2810 directory. That initializes it, and now I can type git status, and it says there are some untracked files, including the directory CS2810-ARM-Mandelbrot. I'm going to say git add dot. That's going to say add the current directory and everything in it. And now when I do git status, it has scanned it and found all these files. And those are all great, so I'm going to commit them. When I say git commit -am, the A part, I'm just kind of in the habit of typing, but it tells it to grab all files that have changed. It won't add new files, but if you have a file already under source control and a change has been made, it will automatically slurp it up into the commit. And then M means I'm just going to type my message right here. If I left that all off, it would pop up an editor and expect me to type my commit message. I'm going to say starting Mandelbrot step 1. So it tells me that it has created 9 new files and so forth. Git log shows me that step is now committed. Git status shows me that nothing has changed since I started working on it. So now I'm going to go into the main directory and look around. There are a few things to note. There's a doc directory. That's the documentation for this project. And if I load doc.md to look at it, that's the documentation in Markdown format. And if you're not familiar with Markdown, it's meant to be it's a Markdown format that looks mostly like a normal text file with a few annotations, and then it can be converted into HTML automatically. If you ever comment on sites like Reddit or blog posts, a lot of blog comment systems now understand Markdown, GitHub, so you're probably familiar with it. So this has the instructions. The same directory also has index.html, which is that Markdown file converted into HTML. So if you're working on a machine and would like to load it into a web browser, that's an option as well. What else do we have in the main directory? We have i2a.s. That's my starter file for the code. And as you can see, there's not much there. There's just a comment saying you should write your code here. There's a make file, and the make file has rules for building and testing. And it's a fairly complicated file. One thing I will note here is if you're running your own Raspberry Pi, if you type make setup after you've gotten this far, that will install all the other tools that you need so you can run things locally. So you have to have root access, so you won't be able to do it on Leghorn. But if you're on your own machine and want to get the other packages that are necessary for assembly language development for these projects, make setup will install them for you. There's a lib directory that has some other files, kind of support files, that we can ignore for now. The tests directory has the unit tests that will be used for grading, and these are the exact same ones that are used for grading on the server. It's some C++ code in a unit with a unit test library, and sometimes it'll be useful to go and read that. There's a lot of stuff you can ignore, but basically whenever it calls regwrapper, it's calling your code and giving it the inputs that you can see here. So here it's giving it a buffer address and telling it to do the number 10. And then if you scan down, it expects the result, n, the number of bytes written, to be 2. It puts a trailing 0 on it, but then you can see here it expects that you've written 0, 1 out to the buffer. That would be a correct result. Then down here's a test where it tries doing a 19 and expects it to come back as 90 to write the string 91. If we scroll all the way down, we have some bigger tests where I give it the number 1, 2, 3, 4, 5, 6, and I expect it to have written 6, 5, 4, 3, 2, 1. So they're just a series of tests. It'll call your code many times and check the results each time. Those are the main things we'll need to look at. So I'm going to, let's see, just copy over a completed version of I to A.S. And if you don't have that yet, watch the other screencast, which walks you through the source to it. Okay, I just did that from another machine, and so now I to A.S has the complete source code. So since I'm on Leghorn, I'm on an ARM machine, the most basic test I'll do is to type make run. That compiles it, or assembles it, technically speaking. Here's I to A, that's my source code. Start.s is the starter test code. Links the results together, and then runs the resulting file, which is called a.out. And here is a big number, and it's jammed together with my prompt because I didn't print a new line. So if we go and look into start.s, we can see the code that actually launched that test, the thing that was running. So we have global underscore start, which is where our code always starts running, so we declare that as a global. Define a few constants for standard out, the system write, the write system call number, and the exit system call number. We go into the BSS segment, which if you recall is where uninitialized data goes. So that's the one that it's kind of part of the data segment, but it's just an amount of space. You can't store files there or store data there in your file. When it loads it, the operating system just sets aside that much space for you. So here we create some space in there, which we've called buffer, and we set aside 100 bytes of space. So that's in the BSS segment. Then we switch over to the text segment so we can write our code. And here is our start code. It's not a function because it doesn't get called normally and it never returns. So it doesn't obey all the normal rules of a function. So I'll normally call it the start block. First thing we want to do is call I to A. The purpose of this start file is to give us something really simple that just calls your code right away, and that will give us an easy connection point when we want to hook up the debugger. So we immediately call I to A. We do that by preparing the two parameters I to A expects. In R0, it should have the location of the buffer. So I do that LDR R0, that means I want to load a register R0 from memory. And I say the value that I want to load is the address of the buffer. By putting the equal sign, the assembler will figure out if it can just translate that into a move instruction, and if not, it will store the address of the buffer in a nearby memory location and generate an LDR instruction that finds it. Same for R1. Here I just put a big number, 13579246880. And then I do a branch with link to I to A. That's the unconditional branch with the link. That means that as it's transferring control to I to A, it's putting the address of the next instruction to run, which would be here on line 21, into the link register. That way when I to A is finished, it has a way of jumping back and returning control to the start block. Once I to A is successfully completed, I expect my buffer to have this in reverse order. So it should have 08642975531. And I want to write that to the screen so that I can confirm it. So I prepare a write system call. The write system call expects a file descriptor number to be in R0. So I move standard out there, the number 1. It expects the location of a buffer to be in R1. So I do another LDR instruction to set that up. And it expects the number of bytes to write to be in R2. So I do that. R0 had the result from the I to A function, the number of bytes that it wrote, so I transfer that into R2 where write will look for it. I had to do that first because here in line 22 I overwrite R0, and I need to make sure that I get its value into the right place before I overwrite it and lose it. Then I move the write system call number into R7 and do SVC number 0 to initiate a system call. So that should write the buffer out to the screen. So I'd expect it to print this number if I to A was running correctly. And then we need to exit. So we prepare an exit system call. I move the number 0 into R0, that's the exit status code, and that indicates success. I load the exit system call number into R7, and then I do SVC number 0. When I run this, and note that I can also cite grind action run to run it on the server. It's just a little bit slower, but I get the same result. It just runs make run for me on the server instead of me typing make run and running it locally. In each case, it assembles everything that needs to be assembled, links what needs to be linked, and runs a.out. And here's the output I was expecting. Remember, the input was 13579-24680, and so it's printing that in reverse. And it does it whether I run it locally or on the server. Right there. And then because we didn't explicitly print a new line, there isn't one displayed, and so the prompt, or in this case the next message, kind of gets mashed onto the end of it. And that's normal. Now, none of this has caused a grade to be submitted to Canvas. So what I'm going to do is do a get status, and it shows me a few things. It shows that I've modified i2a.s. It also shows there's some files that are not currently under source control. I don't normally check in object files. I2a is the result of the assembler processing i2a.s. And start.o is the result of processing start.s. The idea is that I can always just run the assembler again to regenerate those, so I don't need to save them. But I would like to tell Git that it can ignore them. So I'm going to create a file called .gitignore, and in it I'm going to say star.0 and star.out. And that tells it to ignore any file called star.0 or star.o, or a file called anything with a .out extension. I'm also going to go ahead and put star.ppm in there, which will be useful later when we're generating ppm image files, because we don't want to check those in either. I save that file, and now when I do a get status, it notes that there's a new file called gitignore, but now it is ignoring all those other files. I have to add .gitignore to git, because it's just a normal file. And now when I do get status, it says, okay, there's a new file which I added, so this is ready to be committed. It's noticed that I have modified i2a, but I haven't staged it for commit. So I could either say git add i2a.s to stage it, or I can say git commit -am, and the -a tells it to go take all those modified files and automatically add them to the commit. Now if I look at my git log, I can see both of those commits. If I say git status, nothing has changed. The other thing I can do is type make clean, and there's a rule that will just delete all the stuff that was generated. So that gets me back down to, it gets rid of my .o files and .out files and so on. So let's see, once I'm finished and ready to move on to the next step, by the way, I would be careful to make sure you check in your commits before you do a grind grade. Because if you're successful, grind grade will automatically move you to step 2. And I want to capture everything that was there that let me succeed on step 1, because it's going to change some things as it's setting up for step 2. But so now that I've done that, I'm going to say grind grade. And oh, by the way, let's see, my make test is the one that runs all those tests we saw earlier. So I'm going to make sure I do that to test things more thoroughly. It's a little slower because it has to compile some C++ code. And everything ran successfully. Similarly, grind action test will do that same thing on the server. Another side note while this is running, whenever I run grind anything, it saves everything on the server for me. So if I would just want to trigger a save and nothing else, I can say grind save. And it just stores those so that if you were to go and do a grind get somewhere else, it would give you the latest version that you've saved. So now that everything's passing, I'm going to say grind grade, and that's actually going to submit it. It won't give me as much feedback, assuming it succeeds. It will give me the feedback if I fail the tests. But if I succeed, it will tell me as much. Step 1 passed, and moving to step 2. And now if I type get status, I can see that there are some changes that have been made. .grind is a file the code grinder uses to keep track of things. The documentation has changed, including its Markdown and HTML formats. Start.s has changed, and the test code has changed. i2a.s hasn't changed. My i2a is still there. But I'm going to go ahead and do a git commit right now and say starting step 2. This way, if I'm working on step 7 and I remember there was something in the instructions for step 2 that I want to look at, or I want to look at an old version of my code, I can use git to always go back to that earlier version. So I make sure that I commit at the beginning of every step, at the end of every step, and really anywhere else in between where I just want to make sure that I'm not losing anything and want to be able to get back to it at another time. So let's see, git status says everything's good. Now I can go and look at the doc file and see my instructions. And the goal of step 2 is to finish writing I to A so that it reverses that buffer after it's created the string so that the final result is in the proper order. And that will be the subject for another video.